Welcome to the 9th lecture of open course on diffusion in multi-component solids. In this lecture, we will see how Gibbs free energy composition diagrams help in determining phase stability and phase diagrams. We will also see how the constraints are imposed on the degrees of freedom based on Gibbs-Phase rule. So, last class we went over regular solution model and ideal solution models for determining the Gibbs free energy of mixing, that is the change in Gibbs free energy when we form a solution of two components. So, in general, molar Gibbs free energy of mixing delta Gm can be expressed as delta Hm, that is the enthalpy of mixing, minus temperature times delta Sm. Delta Sm is the entropy of mixing. For ideal solution, enthalpy of mixing is 0 and entropy of mixing, the entire contribution to it comes from the change in configurational entropy. So, delta Gm is expressed as RT XA ln XA plus XB ln XB. And for regular solution, delta Hm is given as omega XA XB, and for regular solution this should be regular, and for regular solution we assume that the entropy of mixing is still only because of the change in configurational entropy, and we assume random mixing. So, the entropy of mixing for regular solution is same as ideal entropy of mixing. But in reality, if delta Hm is not 0, then as I mentioned in the last class, there will be a tendency for short range order, and whenever there is a short range order, the entropy of mixing will not be equal to the ideal entropy of mixing, because then the mixing is not random, right. So, in real solutions, the way the Gibbs free energy of mixing is modeled is that we define a quantity called molar excess Gibbs free energy. So, the molar excess Gibbs free energy Gxx is nothing but difference in the Gibbs free energy of mixing of a solution and its Gibbs free energy of mixing if the solution was ideal. So, Gxs is delta Gm minus delta Gm id. In what respect the real solution is different from ideal solution? First, it has a non-zero enthalpy of mixing, and second, the mixing is not random, right. So, the Gxs has two contribution. One is from the enthalpy of mixing and the second one is from the non-ideal part of entropy of mixing, right. So, there are various models on which Gxs can be modeled, and then we can also determine the model for the real solutions. We will not go in details of that. Now, we are interested in understanding the stability of solutions, right. So, if we draw this delta Gm versus composition curve, if the enthalpy of mixing is non-zero but has a very small magnitude, right, then we have seen in the last class the Gibbs free energy of mixing will still be negative at all compositions. And if we draw the curve of delta Gm versus composition expressed in terms of xb or mole fractions of B, it will take a shape something like this. So, we are drawing delta Gm versus xb. Now, I have drawn this curve to be symmetric, right, because I am assuming constant value of omega, right, but this omega may change as a function of composition, in which case the curve will not be symmetric. Okay, but for simplicity, let us just work with the symmetric curves of delta Gm versus xb. So, now what does this mean? That at any composition, if I form a solution, consider xb prime. If I take two components with this composition, xb prime and xa prime, and form a solution, there will be a decrease in Gibbs free energy, and so the forming the solution will be an irreversible reaction. And we see that the solution will be stable at all composition. Now, this is delta Gm versus xb. What about the absolute Gibbs free energy of solution? So, if we draw absolute Gibbs free energy versus xb curve, how would it look like? G solution will be basically the total Gibbs free energy of the system before mixing plus the delta Gm. Right. So, the total Gibbs free energy before mixing will be xa Ga0 plus xb Gb0 plus delta Gm. So, if on left axis is A rich, right axis is B rich, and if I write xb as x axis, then I will have Ga0 marked somewhere on xa equal to 1 axis. This is basically the molar Gibbs free energy of pure A, and Gb0 marked somewhere on the xb equal to 1 axis, right. So, I am showing here Gb0 greater than Ga0, but it can be other ways also. So, I am right now assuming Gb0 is greater than Ga0. So, before mixing, the total Gibbs free energy of the system was xa Ga0 plus xb Gb0. So, before mixing, the total Gibbs free energy varies along this straight line joining Ga0 and Gb0, right. So, this is basically xa Ga0 plus xb Gb0, and at any given composition, if you know delta Gm, then you know the absolute value of the Gibbs free energy, right. So, if we plot at each composition, we will get a curve something like this. So, this is the absolute Gibbs free energy versus mole fraction. So, this is how the G solution versus composition curve would look like. However, we do not know the absolute values of Gibbs free energies, right. So, by convention, we assign value of 0 to some standard state of each component, and usually the standard state is taken as the pure element in its stable state at the temperature being considered, right. So, in this case, Ga0 and Gb0 will assign value of 0, and if we do that, then G solution becomes equal to delta Gm. So, whether we draw delta Gm curves or G solution curves, they give us the same information. Okay. So, now once we have established how the Gibbs free energy of solution varies with composition, right. Our next question is, then how do we determine the individual chemical potentials from there? Any idea how do we go about it? right. So, tangential intercept method, right. So, if we want to determine chemical potential, mu A is basically same as a partial molar Gibbs free energy of A in the solution, and it is defined as partial of Gibbs free energy of solution with respect to number of moles of A at constant temperature, pressure and constant number of moles of B. So, with molar Gibbs free energy of the solution is then written as G solution is equal to X A mu A plus X B mu B, and from the Gibbs-Duhem equation we have X A d mu A plus X B d mu B equal to 0. Now, if we differentiate this equation and then use Gibbs-Duhem equation and do some rearrangement of the terms, we will get the equation for G A bar, which can be written as G A bar is equal to G minus X B times dG by dXB. We can write the same equation in a little bit different form. So, if we write it in terms of G equal to dG by dXB XB plus GA bar, right. This is an equation of a line, right. It is in the form of y is equal to mx plus c, where m is the slope of the line and c is the intercept on y axis. So, here if you see, this is the slope, dg by dxb is the slope of g versus xb curve, right. So, if g is y and xb is x, we will see that this is an equation of the line. If we express the equation for a partial molar Gibbs free energy of A in the form of y is equal to mx plus c, it takes this form g versus xb, and this is basically the equation of a line which is tangent to the Gibbs free energy curve at the desired composition, and G A bar in this is nothing but the intercept of this tangent on the x A equal to 1 axis, right. So, if we want to determine the chemical potential of A at some composition xB, we draw a tangent to the Gibbs free energy curve at that composition, and the intercept on x A equal to 1 axis is basically G A bar, which is same as mu A. Similarly, the intercept of the tangent on the xB equal to 1 axis gives us chemical potential of B mu B, which is same as GB bar. Now, this method we can apply for determining any partial molar quantity if we know the relationship between the actual molar quantity with the composition. So, for example, if we want to determine the partial molar volumes, we draw the curve of molar volume of the solution versus composition, and by the tangential intercept method we can determine the partial molar volumes at the given compositions. Similarly, we can also apply this method to delta GM curve. So, at any composition we can determine the partial molar Gibbs free energy of mixing of a component. So, at this composition, if we need to determine the delta GM A bar, we draw the tangent, and at x A equal to 1 intercept, this is delta GM A bar, and it is nothing but G A bar minus G A 0. it is basically this quantity, the difference between Ga bar and Ga 0. This was the case when the magnitude of enthalpy of mixing was very small. What if the magnitude of enthalpy of mixing is high? So, delta Hm may be highly negative or highly positive. So, let us first consider the case of delta Hm greater than 0 with a large magnitude. So, we have seen when delta Hm is greater than 0 and when it has a large magnitude, delta Gm curve will develop a negative curvature. Now, how do we assess the stability of solutions in this case? So, if we consider any composition towards A rich or B rich side, so suppose any composition towards A rich side here. So, we are drawing delta Gm versus Xb, and if we consider composition Xb1 here, and we see that delta Gm is negative. So, the solution is stable, single phase solid solution is stable in this case. What if I consider so suppose at higher temperature there may be a single phase solid solution at this composition, let us call this Xb2, and if I quench it to this temperature, the temperature that I am considering here. So, initially there will be an metastable solid solution, right, but then will it remain stable? Why? The Gibbs free energy delta Gm is still negative. Right. So, what if the solution with this composition splits into two different compositions? Obviously, in order to keep mass balance, one has to be A rich, the other has to be B rich. So, suppose it splits into two compositions, let us call this A prime and B prime. The total Gibbs free energy now is lying along this line joining A prime and B prime, and where it intersects this Xb2 line. We have seen by splitting into A prime and B prime there is a decrease in Gibbs free energy, right. So, there is a tendency for this solution to split into two different solutions, one with composition which is rich in A, the other richer in B. Now, this can continue, it can further split, right. Instead of A prime B prime, it can split into, let us call this A double prime B double prime, and there is a further decrease in Gibbs free energy. So, what will be the equilibrium compositions of A rich and B rich solutions? How long it can keep decreasing? If we analyze this, we will see that it will keep decreasing until we have A rich solution with composition A, B rich solution with composition B, and these points A and B are basically the touching points of the double tangent to the curve. Double tangent is basically the common tangent to the both parts of the curve. Now, why not beyond A and B? If it splits further, we will see that there will be an increase in Gibbs free energy, right. So, the equilibrium configuration will be two solid solutions, one with composition A which is in equilibrium with another solid solution with composition B. So, any solution in between will split into two compositions. So, at temperature T, any composition between A and B will be stable as two phase solid solution, one with composition A, the other with composition B. So, up to A we say solid solution 1 is stable, beyond B the B rich solid solution, let us call it 2, is stable, and between A and B there is a 2 phase equilibrium 1 plus 2. And you see this compositions are fixed for the 2 phase equilibrium, and why is that? It is also consistent with the Gibbs-Phase rule, right. So, what does Gibbs-Phase rule says? F is equal to C plus 2 minus P, where F is the number of degrees of freedom, C is the number of components, and P accounts for number of phases, and 2 accounts for 2 variables, temperature and pressure, right. So, if we considering binary system, which we are considering here, C is equal to 2, and the number of phases here are 2 in the 2 phase equilibrium region. So, we basically have F is equal to 2 plus 2 minus 2. So, we have 2 degrees of freedom, but we have already consumed that. Why? Because we are drawing this curve, remember, at constant temperature and constant pressure. So, both T and P are constant. So, these 2 degrees of freedom are already utilized. So, in effect F is equal to 0. Okay. So, we cannot vary the composition. So, once we fix the overall composition, that is it, the compositions of the 2 phases in equilibrium is fixed. Okay. Whereas, in the single phase region we will have 1 degree of freedom, right. So, if you see, there is a degree of freedom of composition, you can vary the composition and still be in the single phase region. Now, within this region what happens if I have different compositions? So, as I change the overall composition, what will change, because the composition of the 2 phases are fixed, right. So, the relative amount of 2 phases will change. As the composition moves towards B rich side, the fraction of B rich phase, that is B phase, will increase, and those phase fractions can be obtained by lever rule. Okay. So, now what happens if I change the temperature? Okay, I will redraw this curve here. So, between points A and B there is no miscibility. So, it is called a miscibility gap, right, the miscibility gap region between A and B. If we plot temperature versus XB, we can plot these compositions A and B. So, let us say this is at temperature T1. So, at T1 we plot these 2 points A and B. As I increase the temperature, what should happen? See, delta Gm is equal to delta Hm minus T delta Sm. So, the entropy of mixing factor is multiplied by the factor of temperature, right. So, as I increase the temperature, contribution from the entropy term is increasing, right. So, as I increase the temperature, the miscibility gap should decrease or increase. So, relative contribution from delta Hm is decreasing, right. So, the region with negative curvature should decrease, right. So, as I increase the temperature, so if I draw the same curve at a higher temperature, it will be something like this. And if I determine again the equilibrium compositions by tangential intercept method, this will be say A prime B prime. So, at a little higher temperature, let us say at T2, plot this. So, if I keep increasing the temperature, at some point this curvature, negative curvature will vanish, right. During the transition at somewhere at some temperature T3, the curvature will become 0 at this point, and that is called the critical point. So, at that point basically A prime and B prime are overlapping, and if we draw this curve, this is basically the locus of A and B, we will get basically the phase diagram with miscibility gap, right. There has to be a little curvature here. So, this is how we can obtain the phase diagram from Gibbs free energy mixing curves. This is an example of phase diagram with miscibility gap. At temperatures above this, there is no negative curvature because the contribution from T delta S term is very high, right. So, the negative curvature which was mainly because of the highly positive value of delta Hm has vanished, and so again the complete miscibility will exist at higher temperature. So, beyond the critical temperature, so this is the critical point, this is the critical temperature, which in this case is T3, and the miscibility will be there again. Clear? Any doubt? Okay. So far we consider only one solid solution. What if there are more phases which are stable? So, for example, the simplest of such system is an isomorphous system. So, in isomorphous system there is complete miscibility in the liquid solution as well as complete miscibility in the solid state. So, there is a complete liquid solution, complete solid solution, and there is a two phase region in between liquid plus solid. So, there are two phases we need to consider, liquid as well as solid. So, how do we get to this phase diagram from the Gibbs free energy of mixing curves? So, since there are two phases, we need one curve for each phase. So, we need one delta Gm curve for solid solution, one delta Gm curve for liquid solution, right. So, let us first draw the delta Gm curve for liquid solution. We can draw G solution curves, right. So, that way I can explain it in a better way. So, when we draw G solution curve for liquid, what we do? We take first pure A in liquid form at the temperature which is being considered, and we take pure B in liquid form and mix them to form liquid solution. Now, let us select the temperature T, let us call it T1, in between the melting points of the two. So, T1 is greater than the melting point of A and it is lesser than the melting point of B. So, on x a equal to 1 axis, I have to first locate GA0, the molar Gibbs free energy of A. This is in liquid form, right. On xb equal to 1 axis, I locate GB0 B in liquid form, and then if we find out the Gibbs free energy of liquid solution, you can draw the curve which will be something like this. So, this curve is for liquid solution. Right. We do the same procedure for solid solution. We first take A in solid form, then B in solid form, and then mix the two, find out what is the change in Gibbs free energy. Now, GA0 solid, where would it lie relative to GA0 liquid? It will be above, because at T1 liquid A is a stable phase. So, solid A will have higher molar Gibbs free energy than liquid A. So, GA0 solid will be greater than GA0 liquid. What about GB0 solid? T1 is less than TMB. So, at T1 pure B is stable as solid. So, GB0 solid will be lesser than GB0 liquid, and then we can draw a curve for solid solution, right. This is for solid solution. You see they are intersecting at some point, and we can draw a common tangent to both of them. So, this is the tangent which is common to both the curves. Let us mark the touching point of the common tangent to liquid solution and solid solution as A and B. So, up to A we can see that if we vary the composition from xb equal to 0 up to A, we will see that liquid solution has lower Gibbs free energy than solid solution, right. So, liquid solution will be stable. Beyond composition B up to xb equal to 1, we see that solid solution has lower Gibbs free energy than liquid, and so solid solution is stable. But between A and B what happens? Again, if we consider any composition in between, let us say xb prime, we see that if this composition splits into one liquid solution and one solid solution, it will be associated with a decrease in Gibbs free energy, right. So, at xb it looks like liquid solution has a lower Gibbs free energy than solid solution. One would tend to think that liquid solution is stable, but we also need to think about other possibilities by which will there be any further decrease in Gibbs free energy, and one such possibility is by splitting the same composition into liquid solution which is richer in A and a solid solution which is richer in B, and by doing this we can decrease the Gibbs free energy, and so the one composition will split into liquid solution and solid solution, and the equilibrium compositions can be marked by the common tangent to the two curve A and B. So, any composition between A and B, there is a two phase equilibrium, liquid plus solid, and these A and B can be marked on this phase diagram here, right. So, if we increase the temperature, what should happen? So, will the two curves will shift up or down, or one will shift up, one will shift down? Exactly, both the curves will shift down. Why? We know this equation of state, dg is equal to minus s dt plus v dp, obviously plus sigma mu I d n I at constant composition. So, this will be 0. So, and at constant pressure dou g by dou t is equal to minus s. So, if you consider any composition, as I increase the temperature, the Gibbs free energy should decrease, because the slope is minus s. So, the slope is always negative, the Gibbs free energy should always decrease with temperature, but entropy of liquid is higher than entropy of solid. So, the liquid curve will shift down faster than the solid curve, right. So, in a way it will look like relatively the liquid curve is shifting down relative to the solid curve, right. So, if we try to draw that, we will see that the points A and B, as I increase the temperature, they are shifting, both A and B are shifting towards right, and they are approaching each other, right. Similar to here, if I determine the equilibrium compositions of liquid and solid at a higher temperature T2, this will be A prime and B prime, and this will continue until TMB. Right. And beyond TMB, what will be the situation? Only liquid is stable. So, the solid curve will lie completely above the liquid curve. So, at all compositions, Gibbs free energy of liquid solution is lower than that of solid solution. So, we looked at how to derive phase diagrams from Gibbs free energy of mixing versus composition curves for some simple systems, the one with miscibility gap and also one with isomorphous phase diagram. So, now in both these cases, solid A and solid B, both the components in solid states had the same crystal structure. What if they have different crystal structures? Then it will give rise to little more complicated phase diagrams. One example is the eutectic phase diagram, similar to what I have drawn here. So, this is a eutectic phase diagram between two components A and B. There is a little bit of terminal solid solubility. Alpha is the A rich solid solution, which let us say is BCC, beta is B rich solid solution, which let us say is FCC, right, and there is a eutectic point here, the three phase equilibrium between alpha, beta and liquid. So, how do we get to this from the Gibbs free energy versus composition phase diagram? So, in computational thermodynamics, essentially we evaluate the Gibbs free energy curves for different phases, and then from this Gibbs free energy versus composition data we derive the phase diagram. That is the actual way we go in computational thermodynamics, but to understand the process really well, let us do it a reverse way, right. So, at a given temperature on the phase diagram, let us see how the Gibbs free energy mixing curves will look like. So, let us start with the temperature T1 here, where you have a two phase equilibrium alpha and beta. Now, there are three phases on the phase diagram. So, we need minimum three curves, one for BCC solid solution, that is alpha, one for FCC solid solution, that is beta, and one for liquid solution. So, first we need the curve for alpha, that is the BCC solid solution. So, we need to first mark Ga0 and A solid in BCC crystal structure, and we need the point GB0 and B also in FCC, B in BCC, sorry, we are drawing the BCC solid solution curve. So, B also has to be in BCC. So, note B is stable as FCC, but we need the value of molar Gibbs energy of B in BCC, right. So, we first need to convert FCCB into BCCB and then mix A in BCC and B in BCC to form the BCC solid solution. So, that will give us the curve for Gibbs energy of mixing curve for alpha. So, this is the curve for alpha, right. So, this basically practically it may not be possible to determine the Gibbs energy change associated with this transformation FCCB to BCCB, but we need to know that. So, that may be done by the first principle calculations. Right. Then we need the curve for beta. So, for beta, which is FCC, we need Ga0 for FCC, that is the molar Gibbs energy of A when it is FCC, and obviously A FCC is an unstable phase. So, the value of Ga0 FCC will be higher than Ga0 BCC. And B is stable as FCC. So, GB0 FCC will be lesser than GB0 BCC, and we can get the curve for beta. Right. This is for beta, and we can determine the two phase region by drawing a common tangent. And these touching points A and B mark the equilibrium compositions of the two phases in equilibrium. So, if we see up to point A, there is the alpha stability, beyond point B or beyond the composition B, beta single phase is stable, because Gibbs energy of beta is lesser than that of alpha, and between A and B there is a two phase equilibrium alpha plus beta. So, these A and B points on the phase diagram are really these 2 points A and B. As I increase the temperature, these 2 points will approach each other, right. So, we will see that the solubilities on both sides are increasing. Now, note here one thing, there is a common tangent, right, at A and B. So, if I want to find out chemical potential of the two phases, chemical potential of A and B in the two phases at any composition between A and B, what would it be? We know any composition between A and B will be stable as two phase mixture, one with composition A, another with composition B. So, I need to know the chemical potential of A, for example, in phase A and in phase B, and it will be given by the tangent. So, trivially, since there is a common tangent, right, mu A in A will be same as mu A in B. Similarly, mu B in A will be same as mu B in B, and this is the condition for two phase equilibrium. So, the chemical potential of A in one phase should be equal to the chemical potential of A in the other phase. Similarly, chemical potential of B should be same in both the phases. What about the liquid solution curve? It will be lying above. So, liquid solution curve will be lying above. So, it has to be lying above this tangent line, right. As the temperature increases, the Gibbs-Phase energy of liquid solution is decreasing faster than the solids, right. So, at one point you can imagine this the temperature will come when there may be a possibility that there will be a triple tangent, because this liquid curve relatively is shifting down. So, at some point it may touch the common tangent to both the solid solution, right. So, in that case there is a common tangent and the liquid is also touching so there is basically a 3-phase equilibrium, because in this case chemical potential of A in alpha is same as chemical potential of A in beta, same as chemical potential of A in liquid solution. Similarly, mu B alpha is equal to mu B beta is equal to mu B liquid solution, and this is basically the eutectic temperature, right, because at eutectic temperature you see there is a 3-phase equilibrium here. So, if we mark these A, B and C, these are these 3 points A, B and C is the what we call as eutectic point. So, in this case up to point A single phase alpha is stable, right. Beyond point B single phase beta is stable, and between A and B there is a 3-phase equilibrium alpha plus beta plus liquid. Clear? Okay. So, this way you can assess other phase diagrams also, more complicated ones. Now, let us look at one more case when delta Hm is highly negative. So, what should happen when delta Hm is highly negative? So, when delta Hm was positive, there is a tendency for phase separation, it developed a miscibility gap, right, because delta Hm positive means AB bonds are weaker than AA and BB, average of AA and BB. That means there is a tendency to minimize the number of AB bonds. So, there is a tendency for phase separation, but when delta Hm is highly negative, that means AB bonds are much stronger than AA and BB, which means there will be a tendency to maximize the AB pairs, number of AB pairs. Now, in extreme case what might happen, for example, if you are considering 50% of A and B, when will be the number of AB pairs maximized? Simple, when all A atoms have only B as neighbors and all B atoms have only A as neighbor. So, this is an ordered structure and it may form a completely different phase, which is called as intermetallic or intermediate phase, right. So, when enthalpy of mixing is highly negative, there will be a tendency for ordering and we may develop an intermediate phase. consider such an example. This is an example of a phase diagram with an intermediate phase. We may have A, B, and this is intermetallic AB. So, in that case now we have 3 solid phases, alpha, beta and intermetallic AB. This will have a completely different crystal structure, and then there is a liquid phase. So, we need at least 4 Gibbs free energy curve, one for alpha, one for beta and one for AB. And typically the Gibbs free energy curve for this intermetallic will be very sharp, because delta H mixing is so highly negative that it develops such a sharp delta G mixing curve, right. And then we can draw one curve for alpha, curve for beta, and we can determine the 2 phase regions by the method of common tangent. Right. So, up to point A, if we consider this temperature T1 here, alpha is stable. Beyond this, beta is stable. Now, we can draw 2 common tangents, one between alpha and AB, the other between beta and AB. So, between these 2 points, so this is basically point, let us call this P, this is C, this is D, this is A, B, C, D. C is the common tangent between alpha and AB, touches the curve of AB, and D is the point where the common tangent between beta and AB touches the curve AB. And there is a small region between C and D where AB is stable, it is this small region. So, this phase region is basically alpha plus AB, between D and B we have beta plus AB, and between this small region there is a single phase AB which is stable. Okay. So, when delta HM is positive, there is a tendency for phase separation, delta HM when it is negative, there is a tendency for ordering. All right, any question?